So now I would like to invite Mr. Mustafa Halilsoy for the presentation entitled as From Everyday Physics Problems to Very Big Problems.
Everyday problem. Many of people here may not know what is a black hole, but everyone knows what is this. So I wonder whether you have been interested in the physics of true form. I want to say a few things, and I brought two things with me. I hope that you will enjoy that. I think I am the youngest man here. I am 68 years old. You are all old people here. As the youngest man, I have to prove myself now. So, I brought two things with me. Yesterday we had some talk about the importance of Cyprus historically. And I got a famous book. This book, The Gospel of Barnabas. This is a very famous book. And this is what makes Cyprus a very historic island. And thousands of years to come. So, the author of this book is about 2 kilometers away, St. Barnabas. I hope that most of you have visited that site. So, this version of Bible of Barnabas is very famous worldwide. I have this copy, really, I forgot from where and when I bought it. I have no idea, but after our talk yesterday, I checked from my library and I discovered that it is here. Maybe it is out of print, but I cannot guarantee that it is the original one. So it needs a research for the historians of arts. So, another interesting piece of information that I may start with, it is one of the issue of American Journal of Physics. So, 2007, 10 years old. In this issue, there is an article that concerns physics very much. You see the pyramids on it. So, the article here consists of 3 parts. One part is about the extinction of the dinosaurs. The other part, exploration of one of the great pyramids of Egypt, Khafre. And the third one was about the assassination of JFK. There is physics in all these things. So thanks to the great experimental physicist Halilsoy, who received Nobel Physics Prize in 1968 due to his contributions to resonance particle states. So, you know, I gave this article to one of the historians of arts, Dr. Michael, and next morning he came to me. I saw the extinction of dinosaur problem, the other problem of pyramids, but most interesting came to me the assassination of the Kennedy problem. I said to him, wow, it's very interesting. So, this is exactly a very good physics problem. So you may not remember, but I remember. It was 1963 in November one day that we heard suddenly, I was a young boy, John Kennedy was shot dead in Dallas, Texas, while he was in a parade of a limousine, open limousine. So the limousine was going, there was a sniper at the end of the road, and the sniper shot JFK from the backside of the head. So the head of Kennedy, you know what happened? Went back. This was a puzzle, because those people who did not know physics, they said, there is another sniper, which is in the front building, so he shot at the same time Kennedy from the front. So that is why the head went back. Can you imagine? His head was shot from the back, so normally we expect that the head will go lean on forward, but no, it went back. So this is exactly a very good problem of momentum conservation. So in the newspapers, there were discussions whether there was a second sniper or not in the front. So then Luis Alvarez came to the stage. He made a small research. He said, no, there was no second sniper. It was only one sniper. He shot Kennedy from the back head, but you know, bullet is something very small with very high speed. When it entered into the brain of Kennedy, then a big mass of the brain moved forward, rushed out of the head. So that momentum pushed the head back. So it is like a rebound of the momentum change. Okay. So after this explanation of Luis Alvarez, the problem was solved that there was no second sniper in the game. So this is, you know, momentum conservation is everywhere. From my experience, about 13 years ago, there was an accident here. If you go this road to the main Karpas road, 200 meters away, a staff member from our university, with her car, just was going to the Karpas road. A motorcycle coming very fast from the Karpas road, and there was another car in between that shaded, closed the vision of our staff, our professor lady of the architectural department. So she could not see, so she went out and the motorcycle came, crashed, the motorcycle man died there. So I was called to the court as an expert. What an expert. So, to investigate what was the speed of the motorcycle. So, you know, you have to apply, you have to make some measurements of the road, the traces of the wheels and this and that, whether the car had the ABC system of braking. So don't think that these are very simple things. They are not. The ABC braking system is about the, you want the static friction to stay in action instead of the kinetic friction. So that the wheels will not slide, but still they will rotate. So this is the role of that ABC braking system on the car. Anyway, I made my calculation, I presented in the court, first time in my life. I didn't know in this country, in this city, where is the court? But I had to go, I had to be there, I went there, and I made my presentation. I said the motorcycle was coming at the speed of at least 160 kilometers per hour. So at least, because the friction on the road exactly, you cannot give a number. You can only give some minimum value, so that accordingly you can build on your estimates. I said at least 160. But you know what happened? After a few days of my calculations and coming to the court, the judge decided we don't need these calculations, so all my work has gone in vain. Okay, after I learned that, I told the lawyers, please, another time, don't come to me. I will never act an expert in your court. Okay? Because they will make their decisions. They want to use us something like as a showman. Oh, look, we brought a professor from the university as an expert and so on. Okay? So this was the tragic end of my story with the court. But in the clash problems, you know, it is just a simple collision problem. And these are inelastic collisions, of course, car crashes and so on. And in physics, we have particle collisions, and even some simple systems we can have very elementary examples from inelastic collisions, completely inelastic collisions, and so on. But momentum conservation is, as I had heard from my student times, what I heard, the only physical law that is valid everywhere in the universe is very strong law. Energy conservation may not be satisfied, but momentum conservation is a very strong law that we can rely on even in the car accidents. And now, in recent times, last maybe 5, 6 years, there is a good trend that physicists make collisions of particles near black holes. Because black hole has a very huge potential. So is it possible that you can extract energy? So the original idea of Penrose, 69, sorry. First, it was introduced by Roger Penrose. So from a rotating black hole, it is possible that you can extract energy from the rotational energy of the ergosphere region of the black hole. So also with one of my students, who is not here now, we made some applications, but we made collisions near non-rotating black holes, because you have to make a guess that if you imagine a disintegration of a particle, one running into the hole and the other tending in the opposite direction, then that opposite particle may make a collision with an infalling particle in the field of the black hole, so that we made such a, it is called the BSW effect. So it is a very famous effect, but as I said, mainly it has been studied for the rotating black holes. As with Ali, we had shown that it is also possible to consider it in the diagonal space-times or non-rotating black holes. I am sure some of you are waiting to see the football. Okay, so the football, the mass of this is about 0.2 kilogram plus. Its circumference around 0.4 meter, so on. Now, when a ball moves in the air, there are three forces acting on a ball. Of course, air force, gravity, drag force against motion, and the famous force that is not very well known, Magnus force. That Magnus was a German scientist. He discovered this in the last century, and it acts like a magnetic force. You know, if you send a charged particle into a magnetic field uniform, we teach this in our freshman physics, it makes circles. But in the case of, if you consider this ball spinning and going, then this Magnus force is omega cross V force. So omega is just the spinning direction. Spin, you know, is a quantum term. I don't want to use that, but spinning is, as a verb, we can use it. So if the ball is rotating like this, then we can have a spinning angle like this. And if it is going in this direction, then we have omega cross V as the resulting force direction. So, now what does this mean? This means that if you kick the ball, of course, we are not Roberto Carlos, we are not Platini, or others, we are not Reshat Akolu. He's among us, but he has good kicks. He was, yes. Now he is as useless as myself. So the important thing is that I am sure those who are watching football games, of course this is our standard football, I am not referring to the American footballs, that is different. And this one also, you are familiar with. But the structure on these balls, if you pay some attention, you may ask yourself why there are cells on the balls, and on this one, some lines around. These are made by very serious experiments. Every year, you know, there are some competitions, tournaments. FIFA, the organizer, revises the structure of the footballs, its mass, and the designs on the ball, so that it will reduce the drag effect to a minimum. So if it is spinning and going, then the most important point, when it goes, it turns. So this is the best thing that I am sure all of you enjoy in watching of the football game. You have to make a free kick to the goalie, and there are of course a barrage of rival players. You have to make the kick so that it will go around the barrage, the rival football players, and go into as a goal. You see, so this is the whole trick, and this is just the Magnus force, omega cross V force. There are other detailed parameters. They are like the some numbers, some But as I said, those are obtained experimentally. It is a very complicated matter, to tell you frankly. So I don't want to go into the technical details of that. But in summary, I think if you are interested to learn more, I can advise you some papers. I have one here. It says, David Beckham as a physicist. So this is a very simple, short article. If you are interested to know more about the physics of a football, then I can just give you, and you can study yourself, and you can explore the physics of football further. Okay. So, let us not talk anymore with footballs, but what for, huh? 5 minutes is left. Oh, that is going to kill me. Because I would like to tell you one thing. When you are lecturing, what I heard, what I saw from the greatest physicists, they walk and hands are spinning. This is a scientific result that you can see better. So really, when I noticed that very good physicists are in this stage, they talk and think. So they said we can get better inspiration. Okay. So I will stop. I talk also stop because I will not be able to think anymore. So now, very famous experiments about the recent year. I mentioned two of the detection of gravitational waves. I think this was my first in my career as a physicist 40 years ago. The first thing that I studied was about gravitational waves. But they are non-linear effects which do not exist in linearized version. Okay. So now gravitational waves have been in search for the last 100 years, since 1916. So last year we were excited to hear that, oh, they have been observed by LIGO, LIGO, laser interferometer of gravitational waves thing. And another research was what was called BICEP before that. That was about the second polarization effect of the gravitational waves. In both of the fields, I had two papers. One I had published with Özay Gürtuğ in 2007. Now my idea there was to study electromagnetic waves and see whether they are not gravitational waves indirectly, because you cannot detect the gravitational waves directly. They are so big. But if you can imagine a very strong pulse of gravitational waves, then what I said, an electromagnetic wave will reflect from a gravitational wave partially, and then in this process it will be polarized. This polarization, if you can detect a polarized electromagnetic wave in this space, that may be an indication for the existence of a strong gravitational wave. This was the argument of myself and my former student Özay Gürtuğ. It was completely theoretical. It was an indirect evidence for the existence of the gravitational waves. The other one, on the other hand, which has been discovered last year, and it refers to the coalescing of the collision of black holes, that massive big thing that Eduardo was just mentioning. So when they come together, collide, they give out an extremely outward gravitational energy. So it took billions of years ago, but it was so strong that it reached to our Earth in 2015, 2016, and it seems that this will go on. So they can guess about the magnitude of those black holes. They can guess how much of that mass, after they combine, goes out as gravitational wave. Now there I have a small comment. You know, what I know, the most standard gravitational waves were due to Einstein-Rosen. These were a linearly polarized wave they discovered in 1937. I had discovered in 1987, after 50 years, the cross-polarized version of those waves. But if you notice the LIGO, it is in the L shape. So in fact, because gravitational waves are spin too, they oscillate perpendicularly. Okay? So this is why they made, but there is a point. They should make the platform a rotating one, like the Michelson interferometer. That was a rotating one. But here, it was a very huge setup. Probably it was not easy, but in the coming time, they have to consider it as a rotating LIGO, because that takes into account only the linearly polarized component. But there is another component which is oscillating in between. So that is what I call it cross-polarized. So I hope that one day they will discover that cross-polarized cylindrical wave. That will make me happy. So I don't know, I have too much to say, but I don't want to be busy here also. I may end with, when I was a graduate student, I was taking a French course, because to complete PhD you need another language. I was attending French. The French teacher asked us, "Where are you from? Which department?" I said, "From physics." "Physics? Oh my God! Oh my God!" The other man, he was a teacher also coming to learn French. He said, "Away from physics, you are nearer to God." Exactly, this is what he said. I did not forget this remark. After 40 years, I realized one thing. If you want to discover God, not gold, you need physics. Physics is necessary also for understanding what is God. I have written some comments in the ResearchGate. I hope I will do more. So I am interested in that, because if all these knowledges, physics, mathematics, so many high things, bubble universes, blah, 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 if all these things will not help me to understand what is God, what is life, how did this life come from, what is the use of it? So I think the ultimate question is to discover and understand God. Okay, so now I stop walking and I stop also talking. Thank you very much.
I have one question.
Yes, you can have a look at the Yes.
Hocam, you didn't say what happened to that lady who had accident and you were the forensic expert in the
Well,
court.
she had to stay in the jail for some time.
Understood.
And when I met her after she was released from the jail, she came to me. She was weeping. You know, in the jail, they put me every day to clean the grounds, the rooms and so on for the professor. I said myself, it is very shame for them. They should not do it. So after they released her, she went to her country. She did not stay here.
She was
Polish.
foreigner.
She was a foreigner, yes, from
Polish.
From Poland, yes. So unfortunately, I was involved in that case. It was my first, probably last, my involvement in those trials and so on. Okay, thank you.
Thank you.
So we will have a 15-minute coffee break and then we can come. Thank you.